Hey guys, in our previous discussion, we considered rather a simpler way of expressing matrix, particularly when that matrix stems out of the product of two matrices. We saw that that product matrix can be represented using a single term wherein we involve two categories of indices. Now, in order to understand that, we considered two Jacobian matrices. Of course, there was a reason why we considered the Jacobian matrices, but still we considered two Jacobian matrices. We took the product of these two Jacobian matrices as shown here. And the product matrix that stemmed out of this product of the Jacobian matrices, they are expressed here. And each of these entries are given a specific name depending on their location. Now, when you consider or when you expand each of these entries, that stem from the product of two Jacobian matrices, each of these entries will have three terms that are added together. So ultimately, when you consider this entire matrix here, which has 9 entries in them, to represent this product matrix of two Jacobian matrices, we need to write it or expand it using 27 terms. Now, what we found towards the end of the previous discussion was that these 27 terms that contribute to this matrix here, that is the product of two Jacobian matrices, can be expressed by this single term here. And the way we were able to do that is by introducing two categories of indices. These indices we refer to as the dummy indices and the free or live indices. So free, or it can also be referred to as live indices. Of course, in this discussions, I will be using the term indices and variables rather synonymously. So when I'm able to introduce the dummy variable and the live variable or the free variable, I'm able to express a product matrix that require 27 different terms for its representation using this one term here. So the dummy variable, essentially, it talks about, or it is rather restricted to each of these individual terms. The dummy variable that we introduce to simplify the expression of this product matrix here, it is rather confined to each of these. They play a significant role. These dummy variables, they play a significant role within each of these terms. And the role they play is rather captured by the summation term. So essentially, when we consider each of the entries of the product matrix, they will involve the sum of two terms. So when I consider the entry J11 in my product matrix, the J11 is nothing but the product of this row and this column here. So it will involve three terms, and the first term will be the product of these two, the second term will be the product of these two, and the third term will be the product of these two. And the summation of these three terms can be expressed using the symbol here. Now, what the dummy variables allow me to do is, I can replace, when I'm introducing the summation sign, I'm essentially replacing the indices with a dummy index. And when I'm replacing it with a dummy index, what my notation allows me to do is, it allows me to get rid of the summation sign before my expression. So each of my entries in my product matrix can be expressed in the form of a summation. Now, when I say that I use the specific form of notation, I'm introducing a dummy variable. So the introduction of my dummy variable allows me to get rid of the summation sign. So when I say that I'm using a specific notation and I'm using a dummy variable or a dummy indices, so it allows me to get rid of my summation sign. Now this notation, of course, if you could recollect, we refer to this as, or this is referred to as the Einstein's notations. So when I say I'm using dummy indices or dummy variables in the context of Einstein notation, so what it essentially means is, before the term that I'm considering, which involves my dummy indices, there is a summation sign. I need to introduce it while I'm doing my calculations. Now, as opposed to my dummy indices, there are my free and live indices. So what they talk about is, they describe my entire matrix. While dummy indices or dummy variables are confined to the summation within my entries, my live or the free indices, they go across the different entries within my matrix. Dummy indices, they talk about the summation within each of these entries, whereas my live or the free indices, they go across my entire matrix, and they can be represented, or these different entries can be represented using these live or free indices. Now, the way these live or free indices operate is, when you consider the individual terms that constitute each of these entries. When you consider the individual terms that are written here that constitute each of these entries, the indices that dictate the position of these entries, they assume a specific location in each of these terms. So what we are doing is we are considering each entries within my matrix, the indices that describe the position of my entries. So in this case, the indices, so let's take this case, the indices that describe the position of my entry is 2 and 1. Now when I consider the terms that describe my J21, these indices occupy specific positions in the expanded version. When I consider the expression that corresponds to my J21, these indices occupy specific position, and these positions are opposite to my dummy indices. So these positions are rather the top left and the bottom right. So now when I replace these indices with a variable that is free or the right variable, then when I change these indices, I'm correspondingly changing the entries within my matrix. So I have two sets of variables that I'm introducing. The one variable takes care of the summation term within a given entry. The other variable, it takes care of the different entries within a given matrix. The one that gets across the different entries within the matrix, we call that as a live or free indices. The one that takes care of the summation, we refer to it as the dummy index. When we consider when we rather change the values of my free or the live index, what we are essentially doing is we are changing from one expression to another expression. As I'm changing my values of my dummy variables, what I'm essentially doing is within a given expression, I'm moving across my terms. Whereas when I'm changing my free or my live indices, I'm moving from one expression to another. In other words, within a matrix, I'm moving from one term to another, one entry to another entry within a given matrix. Thereby, I'm able to rather capture all the entries of my matrix. Dummy indices within an entry, live or free indices, it gets across all the entries within my matrix. Now again, we have taken rather the most, in this context for whatever different matrices we can consider, we have taken rather one of the most demanding form of a matrix in the form of Jacobian matrix, and we have considered the product of it, and this we were able to express it using dummy and live indices. So let us try to put our understanding into practice by considering rather straightforward matrices. So let us consider rather matrix A, which is straightforward, and the matrix B, it's a square matrix of 3 cross 3. Now these positions are each of these terms, they do not have any meaning. These are just a simple matrices, simple square matrices, and each entries they are described based on their position within the matrix. So we have our A matrix and we have my B matrix. So now we are going to take the product of our A and B matrix, and the product matrix is going to be C. Now each entries in our product matrix will depend on, or the way we arrive at each of these entries is by taking the product of a specific row and a specific column. For instance, if you want to consider C11, again it's going to be the product of this row and this column here. So ultimately we will be writing our C11 as something like this. So the expression that corresponds to C11 is this, the expression that corresponds to C12 is this, the expression that corresponds to C13 is this, and so on and so forth. So instead of considering complex Jacobian matrices, Jacobian entries, we are just considering, or partial derivative, the entries that are in the form of partial derivatives, we are just considering a simple set of matrices. We are multiplying them and we are ending up with a product matrix, and we are considering each of these terms in the product matrix. And as you can see, there are 3 terms that are associated with each of the entries in the product matrix, and again these are nothing but the multiplications of the rows and the corresponding rows of the columns. Now when I want to introduce my dummy index, all I have to do is look for a way to express each of the entries using a summation. Now the first step is, so ultimately my ultimate goal is to represent this entire matrix using dummy and live indices. That's my the overall objective is to rewrite this entire matrix using dummy and live indices. So in order to do that, first let us try to introduce the dummy index. So when I want to introduce the dummy index, the first step I need to do is rewrite each of these expressions using the summation sign. So when I do that, I'm able to introduce the summation sign when I'm able to introduce a variable that corresponds to these variables here. So when I introduce a variable that corresponds to each these indices here, then it becomes possible for me to write this entire expression using a summation sign. So as you can see, there is a pattern to it, meaning I'm replacing the inner indices with a variable. So in this case, the variable I'm using is I. So I need to express this term C11, all these summations of the term C11 using the summation sign here. So that is possible when I'm replacing the inner indices with a variable I. So I can do the same not only for C11, I can do the same for C12, 13 and so on and so forth till C33. So when I'm able to do that, that is replace my inner indices. So I have two outer indices and I have two inner indices. When I replace my two inner indices with I am able to rewrite these expressions rather using this variable here, that is using the I variable here, that is preceded by a summation sign. Now, as per our description of the dummy variables go, when I say that I'm going to use Einstein notation, so it allows me to get rid of the summation symbol. So ultimately, I can rewrite my individual entries as A1i and BI1 and correspondingly so. So I want to write my entries of the product matrix by involving dummy and live indices. The first step I do is express each of these terms using a summation notation. Now I remove the summation notation because I treat the corresponding variable as my dummy variable, and turns out there is a wonderful pattern, meaning because the dummy variable that allows me to introduce the summation sign, they are in the inner position. So in our previous discussion we saw that lower left and upper right, but in this case now they occupy an inner position. Now when I want to, so this dummy variable has allowed me to consider a given entry with three different terms. Now I want to move across the different entries in a given matrix, so I need to introduce my live or free indices. So these live or free indices, they occupy the position in the outer ring. So my live or the free indices, they occupy the position in the outer ring. And as you can see, these indices, they correspond to the position of the entries. So 1, 1, 1, 1, 1, 2, they correspond to the position of the entry. 1, 3, they correspond to the position of the entry. 3, 3, they correspond to the position of the entry. So it means that it allows us to replace these indices with live or free indices, so that when different values are assumed by the live or the free indices, it means we are considering different entries in our given matrix. So correspondingly, I can write this sets of 9 different entries using an expression like this. So what it essentially means is, when my K and L assumes different value, I'm considering different entries within the product matrix. In the case of I, what I end up having is I end up considering rather these just one entry and the summation within one entry. So essentially, it becomes also possible for us to express the straightforward multiplication of our matrices and the product matrix system out of it. And the way we are able to do is again the same approach of introducing dummy and the live indices. In this case, when we are considering rather straightforward matrix multiplication, the dummy indices assume an inner position, the live indices or the free indices assume the outer position. Again, the dummy indices, they talk about summation within a given entry, whereas the live or the free indices, they move across the different entries. When the live or the free indices assume different values, they talk about different entries. When the dummy indices assume different values, they talk about a given term within an entry. So I hope this rather sorts it out for you. Now finally, we will go to we'll consider one other matrix multiplication, and with that we will wind up our discussion on the Einstein notation. Now let us consider the product of matrix A to that of matrix or the column matrix B. Now of course, if you could recollect, this is how we introduce the Rather, this is a part of the introduction to that of the tensor, because this would be a term that would describe the stress, and this would be the term that would describe the area, which ultimately allowed us to get introduced to the tensor. So this is something that we considered while we introduced the tensor. Now, when we consider the product of these two matrices, of course, you can rewrite we can express the product matrix as C1, C2 and C3. So ultimately, when you consider the individual expressions of C1, C2 and C3, these are written like this. Now, when you want to introduce the dummy and the free indices, so first thing we need to do is express each of these terms using summation. So when I want to introduce summation, I have to replace these terms. Again, in this case, these are the outer terms. I have to replace these outer terms or the outer indices with a variable which we refer to as the, again, dummy variables. So these terms, they contribute to they indicate the summation within a given entry. So this allows me to introduce a dummy variable in the outer position. Now, when I want to introduce the live variable, the only other position left for me is in this case, the inner index, the index that is close to my representation. So that is inner index. So this inner index, it changes with the different entries. So I can use rather my live indices to represent this inner index here. So ultimately, when I want to rewrite this expression, I have two positions. So there is inner and the outer. So inner as just the one index. This inner index, when I vary, it's going to change, get across the different entries. But in the outer index, it's going to talk about, or it's going to describe the summation within a given entry. So it means the inner index that is close to my term A is going to be my live or free index. And the term that is next to it, that is the outer indices, they are going to describe my dummy indices. So ultimately, I can express all the entries of this product matrix here using Einstein's notation as something like this. So essentially, when you consider the Einstein's representation of the matrix, so what it talks about is, so of course we are describing the product matrix here. So what this Einstein's notation talks about is, it talks about individual entries within the matrix. It doesn't talk about the entire matrix as a whole, it talks about the individual entries within the matrix. And these individual entries are rather represented as the product of two entries and the product of a row and the column, and it is the positions of this row and the column that is being represented, or that is getting represented using the dummy and the free indices. Let me repeat, when we are using Einstein's notation to describe the matrix, we are not representing the matrix as a whole, but on the other hand, we are representing the individual entries within that matrix. Now, instead of these individual entries, they have an expanded expression associated with it, and in that expression, we have indices that talk about the summation, we have indices that talk about the position of the entries. The indices that talk about the position of the entries, that vary with the position of the entries, we refer to that as the live index. And the indices that talk about summation within an entry, we refer to as the dummy index. So this live and the dummy index, they essentially allow us to describe the matrices of any dimension using just a single expression. Now this is going to play a significantly greater role, because so far what we have been considering is just a second order tensor. Now imagine how we would have to express the third order tensor without this notation. Let this be a thought experiment. Imagine how would you express a third order tensor in the form of a matrix. Is it possible, or will it be possible for us to do so? So with that, rather we will wind up this lecture. So this lecture has been the implementation of the Einstein's notation that we have considered in the previous discussion, because even though I would like to continue this session, in the subsequent discussion, what we will try to do is, we will try to reach our ultimate goal of building a tensor that is independent of a single frame of reference. So that is something that we will be doing in the next session. So I don't want to rush it up. So that we will take care in the subsequent discussion. Goodbye guys.